Okay, hello everyone. Thank you for giving the opportunity to present the recent results about the hydrogen embrittlement in aluminum alloys. And this is a recent development, especially including the selected processing route that we studied in a couple of years. Then we can start to a little bit check the goals. The first things that inspire us that it's from the initiation of this project was how we can control the hydrogen embrittlement in aluminum alloys. It is somehow a big question always, especially from the aerostructures and also airplanes or something like that. And then there were lots of efforts to battle that or to control that in different kind of procedures. But the initial results show us that it is very decisive and very important to change the processing routes. And it was the initiation of this study. Then we will look to the different processing parameters here, and also we will look to find a solution to complete separation of the hydrogen embrittlement in especially high-strength aluminum alloys, which can be the first results that we reported recently. And then finally also it can be very good to find that how we can design the better and more versatile alloys for the future. Then first, the first result, which you can find it in the published paper, then it was studying the effect of solution treatment temperature, and then we figure out the reason for that, and then it was the segregation of zinc, manganese, and copper into the grain boundaries. We tested that this segregation with different techniques, and then finally we found that this is one of the important parameters we can see, and then you can look here that it's if we compare these two tests, which one is DNG in the dry nitrogen gas, the other one is in hydrogen environment, we can see that the difference can be comparable exactly to the segregation of this alloying element. And then this was happening that in this temperature we have the optimum elongation loss, and then this will show us that how we can control the solution treatment temperature as one of the parameters. And then the next one was changing the deformation. And then we have introduced the pre-deformation to the material, and then we look to the changing in different parameters. Especially, we've seen that here that the distribution of the different kinds of dislocations like GND and SSD can be effective, especially when we consider that the arrangement of the dislocations here, we can see that the arrangement of dislocations can be changed with the core rolling as we expect, and then this can eventually increase the amount of high-angle grain boundaries here, and then this can be another hint for us to look for the processing parameters to develop a hydrogen-resistant aluminum alloy. Then finally, we could see here that that by combination of the TDS and also the other techniques, we found that when we have more deformation here, we will have more trapping by here the high energy trap, which is HAB, and then it can eventually lead to better distribution of the hydrogen if we have these phases. However, we can see how also here that it's SSDs, which is statistically stored dislocations, are here also trap hydrogen. However, it is not too much effective in the behavior because they have middle energy. And then the other point that we consider, it was about the effect of solution treatment temperature plus core rolling on hydrogen embrittlement of 2000 series, which is aluminum plus copper. And then you can see here that see here that we have the different trap sites that we identified, and then with the changing of the solution treatment with the cold rolling, we can see that we have a different distribution of the hydrogen by looking to the TDS. And it is super interesting because it shows us that how we can design the alloy. And then this is a very good step to design a good alloy, especially when you can see that the force peak can relate it to the second phase particle, and then these second phase particles can change with the heat treatment, and then the higher amount of that can be eventually interesting for us to capture more hydrogen, because has the high energy here, as we can see that. And also the result of energy calculation with the Chuan-Lee method, it's really in a good agreement with another work from the guys in UK, Chow and Karneski. And also here we can look to the fracture surface obtained, and then the mechanism here we could understood the mechanism here that can be the cohesion accompanied by void formation. It can be the separation around the second phase particles, and this eventually can be very important to see that how is the size of these particles, which can create or change with the solution treatment temperature, can be effective. And then also we can say that the force peak, as I told you, the second phase particles can be very determinant factor here. And also in the other one, we look to the effect of different the different mixture of the solution treatment and cold rolling is 7000 series. We know that this is the category of the high strength series of aluminum alloy, and then we seen that again with the changing of the solution treatment plus cold rolling, we have the changing in the partitioning of the hydrogen inside the material, and then appearance of additional peak. We have that here with the decreasing of the solution treatment here, we can see with the constant amount of deformation, and then eventually we can see that the behavior of the material can be changed according to that. And here we can look to the fracture surfaces, and then the fracture surfaces can be different, especially when you look to the middle one. We can see that the fracture surface is somehow doesn't have too much effect of hydrogen on that, and then this can be a promising result for us. However, when you look to this heat treatment temperature, 480, you can see that the intergranular cracks, which can definitely as a result of hydrogen embrittlement. And then here again, when we analyze the trap sites, we can look to the high energy traps, especially here that is soluble phase here, and then we can see that with the changing of them, we will have the change of the possibility of cracking around this crack initiation around these particles. The most important factor here can be considered the distance between these particles, and then eventually if we have a lower and then we have the higher amount of hydrogen trapped over there, then it can also relate to the initiation of the cracks and also propagation. And then this also shows us that is how we can control the hydrogen embrittlement behavior with the changing of solution treatment temperature and cold rolling. And then the final one is the effect of surface treatment, and then also surface treatment could be very important. And then we use that shot pinning now, and then it was very useful to see that how we can have the difference in the microstructure. As we can expect, it is also accessible from the other results, and then we can see the behavior, the different behavior with hydrogen and without hydrogen in the dried nitrogen gas. And then finally we can say that the hydrogen embrittlement behavior was improved. Here if you look to the elongation loss, you can see that the unshot pinned and the shot pinned one, the shot pinned one has a considerably lower elongation loss, and this is very also promising technique. Now we are looking to continue this effect of shot pinning on the different materials, especially also on aluminum, to suppress the hydrogen embrittlement with this technique. And then this can be very important, especially for the steels, can be used in future because it's a common technique for the tubes that usually used for the shot pinning. And then if you want to have a conclusion, then this is definitely can be a good technique to change the processing roads, to improve the mechanical properties, and at the same time we'll have a better hydrogen embrittlement resistance. We've seen that we found the complete separation of the hydrogen embrittlement in these alloys, especially when we have that in 7000 series aluminum alloy with 440 degrees Celsius of solution treatment. And then this is somehow very novel to use that in different cases. Also, as I told, the surface treatment like shot pinning can be a very good way to avoid the diffusion of the hydrogen inside, and then it can be a very good technique to avoid the hydrogen embrittlement. Also, this is not including in this presentation. However, we have another results with the addition of the zirconium to the 7000 series aluminum alloys, and then we had it was published recently, and this is a very promising method with the addition of the zirconium, which can form the zirconium aluminide. Then we will have the 100% of hydrogen embrittlement suppression in aluminum alloy, and then this is somehow that can be considered as one of the most important improvement in the field of hydrogen embrittlement in aluminum alloys. Thank you very much.